So what we want to do is talk about free energy, and to deal with this, we want to talk about the Gibbs equation. So J. Willard Gibbs was a Yale professor of mathematics and came up with this idea about how we can calculate free energy in equations and under particular temperatures and pressures, which is very limited variation in living things. So the idea that this works really, really well. And it's always been for me kind of, how much of this do we need to know? I'm going to tell you, I want you to know the equation. I want you to know what it stands for. I'm not going to have you work the equations. You can take classes. There was at Cal Poly Pomona. There's Dr. Arnold taught one. And really worked at the energetics of living things. But I do want you to know the equation, and I want you to know what it stands for. So we'll look at these. So let's talk about delta G. That's a change in free energy. That's the amount of energy that's available actually to do work. And then we have delta H, which is the change in total energy, which is called enthalpy. Enthalpy is the total energy of a system that, in theory could do work. And so delta G is what is available. So from that total energy, we're going to subtract delta S. S is the entropy, and that is disorder. That is how much we're losing. And that is actually changes depending on temperature. So this equation was done in absolute temperature in Kelvin. So what I do want you to know, again, is the actual equation and what everything stands for. What we'll do is we'll go through and look at some different types of equations. What I do want you to know, free energy and metabolism. Free energy, again, is the portion of a system. Systems, and that should be apostrophe S, energy that can perform work. And then metabolism, which I mentioned in the last one, is the total chemical reactions in an organism. So here we have some ideas, and what I want you to notice is there's two terms here that we'll explain: exergonic and endergonic. So exergonic reactions are ones that release energy, and endergonic reactions are one that require energy. Other exo terms you might have heard, like exothermic, that's talking about temperature. So exothermic are ones that release heat, and then endothermic are ones who require heat. But anyway, so that's a concept, and I'm really showing you this. And the reason I've decided that the Gibbs equation is probably important is because if you look at the little equations over here, you can see when the delta G is less than 0, it is considered an exergonic reaction. So if it's negative. Here, if the delta G is positive, that means it requires energy. And reading over peer-reviewed journals and things, what you'll see is often those, sometimes, depending on obviously the topic, they'll be talking about delta G's. And so I want you to realize what those numbers mean. So what we're going to do is give you, here's an exergonic reaction. We're going to talk. So again, it's one that releases energy. I'm going to give you a bunch of terms, just kind of, this is from the book and then also from other places. When you hear these terms about reactions, you want to think of exergonic. So again, negative delta G, we just mentioned that. Spontaneous, which means that they just happen. They're spontaneous reactions. They don't require anything. They are often called downhill. Basically, there is more energy in the reactants than the products, which is the next statement. And then an example of that would be cellular respiration, where you are breaking down. Cellular respiration is basically ATP. And so here it's a negative 686 kilocalories per mole. That's the amount of energy. And then breaking down ATP into ADP. So ATP we're going to talk about a little bit later on another little clip. Adenosine triphosphate is broken down into adenosine diphosphate plus a phosphate, and that would be a negative 7.3 kilocalories per mole. So cellular respiration, again, would be breaking down glucose and producing ATP, basically. and then ATP breaking down so into the two components. So that is what I want you to know for exergonic. And then you should be able to do the endergonic. So if you think about it, it's going to be requires energy, positive delta G, non-spontaneous, uphill. So that's really kind of the other side of the coin. And then you can see here, cellular respiration, again, taking glucose and breaking it down eventually into ATP. And here you're taking light energy and you're basically building it up to build glucose. So you can see that they're mirror images with the numbers. And then ADP, and you're adding a phosphate, 7.3 kilocalories per mole. All right, so that really is kind of the gist of what I want you to get from the Gibbs equation.